Hello friends, continuing with the chapter electric potential and capacitance. Today we come to fourth part of this chapter, that is Venn diagram high voltage generator and particle accelerator. We will study this topic in two parts. First we will see how high voltage is generated, and in the second phase we will look into how particle acceleration is carried out, or how it can be used for particle acceleration. First we take up Venn diagram high voltage generator. Point by point we will proceed. First, principle. Whenever a charged conductor is brought into internal contact with a hollow conductor, whole of its charge is transferred to outer surface of hollow conductor, irrespective of the charge already present. I repeat, whenever a charged conductor is brought into internal contact with hollow conductor, whole of its charge is transferred to outer surface of hollow conductor, irrespective of the charge already present. You see here, this is hollow conductor and this is a charged conductor which is brought into internal contact with it, and whole of its charge is transferred to outer surface of hollow conductor, irrespective of the charge already present. What does it mean? It means electric potential inside hollow conductor is higher than the electric potential at the outside surface, because charge always flows from higher electric potential to lower electric potential, like liquid flows from higher gravitational potential to lower gravitational potential. The same way, charge also flows from higher electric potential to lower electric potential. It means electric potential inside the hollow conductor is always higher than the electric potential at the outside surface. Now we are to give proof of the principle, whatever we have stated above, that we are to prove. Now first, physical situation. Consider a hollow conducting sphere of radius r having charge q uniformly spread over it. Let another charged sphere of radius r having charge q is brought into internal contact with the hollow conducting sphere, with their center coinciding with each other as shown in diagram. Note 2. Consider outer hollow conducting sphere of radius r. Whole of its charge q can be assumed to be concentrated at its center. As we have learnt in Gauss theorem, that whole of the charge on the surface of hollow conducting sphere can be assumed to be concentrated at its center. We have to apply that result here and state that the charge q can be assumed to be concentrated at its center. Therefore, electric potential at surface point A, this is surface point A, will be, say, VA outer is equal to K naught Q by R. Let us mark it as equation 1. Now VA outer, outer means it is the outer surface of the hollow conducting sphere with radius capital R. Therefore, electric potential at surface point A of hollow conducting sphere will be, say, VA outer equal to K naught Q by R. So let us mark it as equation 1. Now also electric potential at any point inside it, say at point B, this is point B, this is point A, here we are talking of point B now. Now also electric potential at any point inside it, say at point B, will be same. Say VB outer means due to outer shell, electric potential due to outer shell. So VB outer is equal to K naught Q by R. Let us mark it as equation 2. Because electric field inside hollow conductor is always 0, that means V is constant at every point inside hollow conductor, because E is equal to dV by dr, and when we put it equal to 0, it means V is constant according to differential calculus. Now 3. Consider inner sphere. Whole of its charge Q, this charge Q, whole of its charge Q can also be assumed to be concentrated at its center. Therefore, electric potential at point A on surface of outer sphere will be, say, VA inner, that is electric potential V at point A due to inner shell will be equal to K naught Q by R. Let us mark it as equation 3. And electric potential at point B on surface of inner sphere will be, say, VB inner equal to K naught small q by small r. And let us mark it as equation 4. So this is how we can write electric potential. Fourth, total electric potential at point A is equal to VA due to outer shell plus VA due to inner shell, or VA due to outer shell plus VA due to inner shell is equal to K naught capital Q by capital R plus K naught small q by capital R. Let us mark it as equation 5. Fifth, total electric potential at point B is equal to VB due to outer shell plus VB due to inner shell, or VB due to outer shell plus VB due to inner shell is equal to K naught capital Q by capital R plus K naught small q by small r. Let us mark it as equation 6. Sixth, electric potential difference between points A and B. Now carefully look at equations 5 and 6. Let us have a look. Equation 5, here you see there is difference in second term. There is difference in second term of radius only. Okay. Now since small r is less than capital R, therefore electric potential difference at B is more than electrical potential difference at A. Therefore we subtract to calculate electrical potential difference. Now VB minus VA. Now VB minus VA is equal to K naught capital Q by capital R plus K naught small q by small r minus within bracket K naught capital Q by capital R plus K naught small q by capital R, bracket closed. And here we see this K naught Q by R and K naught Q by R will cancel on opening the bracket, and this plus will become minus. And finally we get VB minus VA is equal to K naught small q by small r minus K naught small q by capital R, or VB minus VA is equal to K naught small q by small r minus K naught q by capital R. Let us mark it as equation 7. Seventh, conclusion. Now consider equation 7. Vb minus Va is equal to K naught small q by R minus K naught small q by capital R. Now capital R being more than small r, subtraction therefore is positive. Therefore, electric potential V due to inner sphere is more than electric potential V due to outer sphere. Hence, electric potential inside a hollow conductor is always more than the electric potential at outside surface. It is therefore, whenever a charged conductor is brought into internal contact with a hollow conductor, whole of its charge is transferred to outer surface of hollow conductor irrespective of the charge already present. I repeat. Therefore, whenever a charged conductor is brought into internal contact with a hollow conductor, whole of its charge is transferred to outer surface of hollow conductor irrespective of the charge already present. Okay. Now assignment 2.4, question number 1. A charge Q is distributed over the surface of two concentric hollow spheres of radius small r and capital R. Capital R is very large as compared to small r, such that their surface charge densities are equal. Derive the expression for the potential at their common center. And it would be equal to capital R plus small r bracket close sigma by epsilon 0. Okay, where sigma is surface charge density. Now question number 2. 3 concentric metallic shells A, B and C of radii small a, small b and small c, where A is less than B is less than C, have surface charge densities sigma, minus sigma and sigma respectively as shown in diagram. A. Obtain the expression for the potential of each shell A, B and C. B. If shells A and C are at the same potential, obtain the relation between small a, small b and small c. And the answer would be small b into a square minus b square bracket close. It is equal to c into b square plus a square bracket closed. And you solve and establish this relation on the basis of the text that you have learnt. Okay. Thank you so much. Next time we'll take up next part of it, that is high voltage generation and particle acceleration. Till then, goodbye.